Hello everyone, my name is Vasudev Gohil. I'm from Texas A&M University, and today I'll be talking about our work called AttackGNN. The idea of our work is to evaluate the robustness of graph neural networks used in hardware security. This is a joint work between Texas A&M University and University of Delaware. So let's begin. I want to start by talking about semiconductor-based devices and the threats they face, in particular hardware security-oriented threats. And more specifically, I want to talk about threats due to globalized supply chain. So this diagram over here illustrates what I want to talk about. So for example, let's say you want to design a processor for your mobile or for your laptop. Typically, the designer essentially starts the RTL specification at one point. IPs are integrated from somewhere else, the fabrication happens in a different part of the world, and then integration happens somewhere else, and the end user is in a totally different place. So due to this globalized supply chain of semiconductor devices, there can be security threats such as these. Examples of these threats include hardware Trojans, where a malicious entity can inject backdoors into your processor, or an attacker can reverse engineer your circuit and figure out your IP. So these are the kind of hardware security threats that I'll be talking about today. Now to address these threats, researchers have recently proposed graph neural network-based techniques. The idea makes sense because circuits essentially can be represented as graphs, so it's a natural fit to use graph neural networks, or GNNs, to try and address these problems. Now examples of these techniques are from both ends, defense and attack. For example, people have used graph neural networks to detect and locate hardware Trojans. They've also used graph neural networks to reverse engineer circuits. People have also used GNNs for detecting piracy or similarity between two different net lists. And these GNNs have shown tremendous accuracy. For example, you can see in the last column on the right, they have close to 100% accuracies and true success rates on all of these problems. The question that we ask is, how robust are these GNNs? And to answer that question, we devised this technique called AttackGNN, where the idea is we want to test the robustness of these GNNs using reinforcement learning. All right? Now, before I begin and talk about what AttackGNN does, I want to just clarify the threat model so we are all on the same page. So the threat model that we use is a standard threat model used in adversarial attacks. So an example of an adversarial attack is shown on the top right corner. So let's say there's a neural network that classifies traffic signs. For example, if you give it an input of a stop sign, it will tell you that this is a stop sign. Now, what can be done is if you perturb the stop sign image in a specific way, you can actually fool the neural network into classifying it as a speed limit sign, which is shown on the figure over here. So these kind of attacks are called adversarial attacks, where by perturbing the input to a neural network, it can result in misclassification. So that's the kind of attack that we'll talk about today. More specifically, let's say we have a trained graph neural network. Suppose this graph neural network, or GNN, is trained to detect hardware Trojans. The first assumption that we make is that we cannot perform any modifications to this trained GNN. We take it as it is. We are not allowed to change its parameters. We are not allowed to fine-tune it. We are not allowed to do anything to it. The second assumption or the constraint is that these perturbations that we make to the input, which is the circuit in our case, cannot be arbitrary. We need to follow circuit design rules. We cannot essentially have a combinational loop, for example. So that's the second constraint. We need to follow these circuit design rules. And the third constraint that we have in this threat model is that we only have black box access to the GNN. So like I said, again, we cannot access the the parameters of the neural network, such as weights and biases. We cannot even access the internal architecture of the network. All we have is a black box that you can query and get responses from. So these are the three main constraints that we have in our threat model. And our goal is to achieve misclassification. So that's shown in this figure on the left side. So let's say you have this blue original circuit, which is represented as a graph. If you pass that to the trained GNN, the result is a green tick, meaning it classifies the circuit correctly. But what we want is, as an adversary, we want to perturb that circuit in such a way that the GNN misclassifies it. So an example of this could be, let's say I have a Trojan inserted circuit. I have inserted a Trojan in AES, for example. Now, if I were to just simply pass that circuit to a GNN that was trained to detect Trojans, it will do a pretty good job. Almost 98 or 97% of the time, it detects a Trojan correctly. But if I perturb the circuit specifically, while still preserving the Trojan functionality, I can actually result in misclassification by the GNN. So that's the whole idea of what we want to do. All right? Okay, so let's begin by let's talk more about what AttackGNN does. So like I said, this is a reinforcement learning based technique or RL based technique. So RL typically has two components. There's an environment and there's an agent. The agent interacts with the environment through actions, and in turn, the agent kind of evolves in space, in the environment space, through the notion of state space. Also, based on the actions, the environment provides certain feedback signal or reward to the agent, which the agent uses to guide its future actions. So that's the whole idea of reinforcement learning. Now, what we want to do is we want to map the problem of perturbing or adversarially perturbing circuits to this RL problem, all right? So first, let's talk about the environment. In our case, we model the environment as the circuit that we want to perturb. Let's say it's a Trojan infested circuit. We want to perturb this circuit so that it results in misclassification. So that's our environment. Now we define the state as certain properties of the circuit that we are targeting. So for example, the state vector is a feature vector of multiple dimensions. It can have things like number of inputs of the circuit, the number of outputs that the circuit has, the number of gates, wires, different kinds of gates, counts of different kinds of gates. These are the different features that we consider as our state of the agent. Now for action, we define the action as what is called a circuit transformation command. So an example of a circuit transformation command is, let's say, rewrite action in the open source ABC compiler tool. So these are synthesis directives or commands that can be used to restructure circuits. Another example of an action could be refactor, which is again a command in the ABC synthesis tool. So that's how we define the action, circuit transformation commands that can alter the structure of the circuit without changing its functionality. All right? And finally, we define reward. It's trivially defined based on just how well the adversarially perturbed circuit is. So if our perturbed circuit is able to evade detection or result in misclassification, we give it a positive reward, which is alpha in this case. Otherwise, we give it a 0 reward. So now what happens is when we train this agent in this iterative fashion, let's say we start off with a Trojan inserted circuit, and we ask the agent to pick an action. Let's say it picks the action rewrite. Now we apply that action to that circuit, create a new circuit which is functionally equivalent to the original one but structurally different. We pass that circuit to the GNN that is trained to detect hardware Trojans. And then we use the feedback from that GNN to kind of provide reward to the agent, which again goes on in an iterative cycle to improve its actions in future iterations. All right? So this is the basic premise of our technique called AttackGNN. Now, when we actually ran this technique on a bunch of GNNs, we faced some problems. The first problem is that the actions that we defined, which are the circuit transformation commands, don't really change the structure of a circuit a lot. And this is because these circuits are really optimized. Just performing rewrite or refactor operations will change a few gates, but not a lot of gates. So essentially what ended up happening was that the differences, the perturbations that we needed to evade the GNN detector were not sufficient. So that's the first challenge. The second challenge is that this reward computation, which involves querying the target GNN, is expensive. It takes a few seconds to query the target GNN and get the feedback. And doing this at every step takes up a lot of time, which increases the training time for the agent. Right? And the third challenge is that in this entire formulation, again, because the reward is guided by a specific graph neural network, this agent is only trained to evade that particular GNN. So if, for example, if you are focusing on a GNN for detecting Trojans, this agent will only learn to evade GNN for detecting Trojans, which is not ideal. We want to have a generic agent that can do multiple things or evade multiple GNNs simultaneously. So to address these challenges, we propose 3 solutions. The first solution is what we called effective or generalizable actions. And again, the idea over here is that we want to devise actions that result in more structural variation in the resulting circuit, right? So what we do is we have these synthesis constraints that we incorporate into our action space. For example, let's say we have an action that says, don't use any 3 input AND gates in this synthesis step. So what that essentially does is if there are 3 input AND gates in a circuit, it will replace them either with 2 input AND gates or 4 input AND gates or whatever AND gates are available in the library. It might even replace it with an AND gate and an inverter, right? But the essential idea is that it doesn't use any 3 input AND gates in that part of the circuit. So essentially, instead of having these circuit transformation commands as actions, we have this allowed or not allowed gate types as actions. And what we observed was that this definitely increases the structural diversity that we need to create sufficient perturbations. So that's the first solution. The second solution is, like I mentioned, to combat the long training times because of the reward computations. So essentially, instead of computing the reward at every time step, what we did was we computed the reward at the end of an episode, let's say after 5 time steps. So there's a trade-off between accuracy and runtime. And essentially what we observed was that we can trade off some amount of accuracy and gain a lot in terms of runtime. So that's the second solution that we do to make it more practical. And the third solution to combat this issue of the RL agent being specific to a particular GNN is to use contextual formulation. Essentially what that means is that we add a context to the agent depending on what problem it is targeting. So let's say if the agent is designed to evade GNN for detecting Trojans, then we add a specific context which is encoded as a binary vector, and then the agent only learns for that context, and then we again train that same agent on a different context, let's say for detecting IP piracy. So essentially we combine all of these different GNN techniques into a single agent using different contexts, and essentially what ended up happening is we learn a single agent to evade multiple of these GNN techniques. You can read more about these solutions and challenges in our paper if you're interested. Right? Now I want to focus a little bit on the results that we obtained. So first, let's talk about GNN for IP. So GNN for IP is a graph neural network for detecting IP piracy in hardware circuits. So what I've shown over here are on the x-axis are different circuits that this graph neural network was trained on. Now what I'm trying to do is using our technique AttackGNN, I'm trying to modify these circuits such that GNN for IP misclassifies them. Now, the score for GNN for IP is in the range of -1 to 1. It's a similarity measurement technique, 1 being very similar and -1 being not similar at all. And essentially what ended up happening is that when we perturb these circuits, all these circuits that I've shown here using our AttackGNN technique, we are actually able to evade GNN for IP for all of them. And not only just once, we are actually able to create multiple variants of each circuit that evade GNN for IP for all the different circuits that we tested. Similar results are also true for this technique called Trojans, which is a graph neural network for locating hardware Trojans in circuits. I'll not go into all the details of the benchmarks and the results, but the idea is that essentially for all the circuits that we tested, we were actually able to evade Trojan Saint into essentially Trojan Saint said that the Trojan is in a different location versus where it actually is, simply because we were able to perturb the circuits well enough. And then we have similar results for other techniques as well. For example, we have similar results. There's a GNN technique called GNN-RE, which is used for reverse engineering circuits. And again, we were able to successfully evade GNN-RE for, essentially, there is a full GNN-RE for all of the circuits that we tested. I'll not go into all the details of all the results, but the key idea is that we were actually able to evade 5 different GNN techniques using a single RL agent on all the circuits that we tested with a 100% success rate. Essentially, all the circuits were able to evade all the GNNs that we tested. And the bottom line that I want to say over here is that the graph neural network techniques that have been developed for hardware security for the past few years have done a great job at in a regular setting, but when they are tested in an adversarial setting, when an adversary perturbs the circuits, these GNNs need to do a lot better. Essentially, we need to incorporate methods like adversarial training to ensure robustness of these GNNs. Yeah, that's all. Thank you.